I'm going to talk about OctopuScheduler. As already mentioned, it's a DNN scheduling framework. It's on chip for the Spinnaker 2 multiprocessor system on chip. And what have we developed is basically a framework for the execution at the moment of single DNN layers on Spinnaker 2. We're currently extending it. And it's focused on on-chip scheduling. So we avoid the communication between the host and the chip and try to run the scheduling entirely on the chip. And we also developed within this a hardware-aware strategy specifically for the chip for automated tiling. So there are always different possibilities how you can partition layers. And of course, you need to select one that you run on the chip eventually. This is something we've been looking into. And we've also been looking a bit into the optimization. Here, what I will present shortly today is the reordering for the convolution, so we avoid DRAM transfers. Why? I will come to this in a couple of minutes. So shortly about the hardware architecture, you might have already seen this once or twice, but this is the Spinnaker 2 chip here. It's basically a multiprocessor system on chip platform. It's a many-core architecture. You have 152 processor cores on the chip. And each of the cores has such an architecture where the centerpiece is an ARM Cortex M4 processor, and you have different extensions to this. What's central for our application is the MAC array, which is basically, you can imagine it as a SIMD engine running up to 64 computations in parallel for matrix multiplications and convolutions, which we use to accelerate basically the execution of matrix multiplication, convolutions, and related operations. So this is the hardware architecture that we're working on. And now the question is, how can we execute deep neural network layers on this neuromorphic chip? And one thing you have to do first is you have to think about the tiling. So how do we actually distribute the layer communications? If we have multiple cores, what data goes to which core and what core computes which part of the output result? So for example, for this matrix multiplication here, you would basically partition the inputs and the weights, and then you would arrive at different output tiles here. What we do then is we define certain states that these operations need, which is, for example, you need to load first some start addresses where the operands actually are in the DRAM, for example. You need to load inputs, some preparation maybe. You need to load the weights, then you can run your operation, and you need to store back the result. So it's entirely this whole layer happening as a closed implementation here. And this is a overview of the control and data flow. So what's happening here is that we say we want to run this single layer, and we want to run it as an experiment for verification to see if the scheduler works correctly. So we transfer the data to DRAM, it lies there, and the configuration is stored in the PEs. And then from the host, we trigger the scheduler, which basically orchestrates. It's kind of the manager that orchestrates the other PEs that basically run the layer, which we call workers in this case. So the host triggers the scheduler on the chip, and then the scheduler triggers these workers, which start to load the required data, run the computation, and once they're finished, they give a signal to the scheduler that they finished. And once all workers finished, then the layer is considered also finished. So this is roughly how this works. And now the question, how do we actually distribute the computation? So this leads us back to tiling. How can we actually do this? As you can imagine, there's a large number of possibilities how you can tile such an operation. And this leads us to a large tiling space. And the question is now, which configuration do we select for the implementation on the chip? And what we came up with is we are basically looking at a list of dividers of the input dimensions. So the input height, which is M in this case, and the output width, which is P in this case. We look at the list of dividers of these figures, and a list of dividers of the product of these numbers for the possible number of worker PEs. And this gives us, it spans a parameter space. And this can contain tens or hundreds of possible configurations for tiling. So we need to sort some out for which we have hard constraints. For example, we always want an integer number of processing elements. We also want the layers to fit into the SRAM of the processing elements. So these are hard constraints. If this is not fulfilled, we will just kick out the configuration. And then after kicking out the not possible configurations, we still have a couple of configurations from which we need to select one. This we do via soft constraints. So we sort basically on different criteria, we sort the remaining configurations. And for example, we can sort them by the degree of parallelization. So how many processing elements are actually used. We can maximize this. So we have the maximum parallelization. This is one optimization strategy. And based on this, we then select what we think the best tiling strategy is. Okay, so how does this actually look like when we execute it? What you can see here at the moment, you can see that the blue parts here are related to loading and storing data. These are DRAM operations, which are especially bad. This is also a thing we are working on right now for the optimization. And what this basically, we've been looking into this, how we can avoid this when we implemented the convolution. So there we started already with an optimized approach. How you can tile a convolution, I will just shortly go over this, is basically you probably want to tile along the input height and output channels and maybe along the input width if necessary. So you arrive at such a tiled output tensor along height, channels, and possibly width. And when you think of this, you receive this from a previous layer, then you want to reorder these output tiles of the previous layer because they don't necessarily match the required input tiles for the next layer. So you need to rearrange a bit. You might need to do some padding and to recombine basically these output blocks of the previous layer for the input blocks of the current layer. And this is where we came up with this set of reorder PEs on the chip that basically do this. They take care of this reordering entirely on the chip. So we just have SRAM transfers instead of the DRAM transfers. So we avoid the DRAM communication here. And this really saves a lot of time. Eventually, we want to transfer this also to the matrix multiplication. And this is how this looks like. So the scheduler always defines the start and end of a layer. And for the dedicated reorder PEs, they first fetch the output results from the previous layer, reorder them. And once these input tiles for the next layers are prepared, we can start with the worker PEs for the execution here. And in comparison to the matrix multiplication, you can see that this red part, the execution has it's more balanced here. So we also hope that this will be a good improvement for the matrix multiplication. The convolution is just where we tried this first. And as a short summary, what have we developed? We have currently developed a framework for the execution of single layers of deep neural networks on the platform. It's an on-chip scheduling approach. We developed a specific tiling strategy that also considers, for example, the dimensions of this machine learning accelerator, this MAC array. And we are looking into how we can basically avoid the costly DRAM transfers here. What we're currently doing, we're extending this for multi-layer implementation, and we want to apply this to CNNs and transformer architectures. These are ongoing efforts at the moment, and we're close to finishing the transformer implementation here. And we're of course looking into optimizations. There's on many levels of the system space for improvements, and we're also looking how we can basically pipeline this. What has not been covered in this presentation is there are also different other layer types implemented. For example, the softmax addition and layer normalization that you would need for residual networks or transformer architectures. We optimize the tiling for matrix multiplications. And there's also the details of the on-chip reordering of the convolution, which I just explained shortly now. But if you want to find out more details about this, you can find it in our paper, which is this one. And in the name of all my co-authors, we would like to thank our sponsors who made this possible. And we would also like to thank Spin Cloud Systems for the discussion and the support. So thanks for your attention.